Bueno, días a todos. Bienvenidos de nuevo al seminario del Departamento de Geociencias. Hoy pues, tenemos el gusto de tener con nosotros a Eloís Bessier. Eloís es investigadora del Instituto Francés para la Investigación del Desarrollo, IRD en Francia. Ella obtuvo su PhD en la Universidad de Orleans, Francia también. Y está comenzando a hacer un trabajo colaborativo aquí en la Correa Central. Varios profesores aquí en el departamento. Entonces, bienvenida Luis, la charla va a ser en inglés y hice la introducción en español. Bueno.
I will speak in English, sorry, I cannot be in Spanish. So my name is Geociencias, and today I will talk about relationships between thermal regime and deformation. We are not the only one person working on that topic. There is many people working on that because thermal regime is really an important parameter. If we Yes. Why we are studying thermicity? Because it's an important parameter in Earth dynamics and linked to the atmosphere. If we are on this figure, we can see that the main parameter controlling the plate dynamics is the temperature. Yeah, you are on the scale from this figure. Okay, we have this very important parameter, and we can observe a close link between thermicity and deformation. As we can see on this map, we have most of the major active volcanic zone and most of the geothermal sheets located along the plate boundaries. And what we can also see is a close correlation between geothermal systems and specific dynamic settings. For example, here you have many geothermal fields all along these subduction zones. One question that could be interesting to answer is the interactions between deformation and localization of thermal anomalies, and we can investigate the impact on fluid circulations. Why study the type of question is mainly because we can say that there is many applications to study these things, but one important is to learn more about the hydrogeothermal systems and to better construct this thermal structure from the Earth's surface. Some researchers focus on the heat flow topic. Heat flow is a calculation combining thermal gradient and thermal conductivity. On this map, you have the compilation of all available measurements. The color and shape of symbols are related to the age of acquisition. And if we consider the two main databases compiling these measurements, we reach between 73 and 91,000 measurements. What we also can see on this map is the very heterogeneous coverage of the measurements. And this is a very poor coverage, especially if we have a look on very high resolution reading. If we consider 0.5 degree of resolution, we only have 8% of the Earth's surface which is covered by the measurements. This leads the researcher to ask how to exploit and extrapolate this data. There is many approaches, but I just show you two different approaches. The basic one, the first one, on only one proxy approach. It's okay. We use a specific geological and geophysical data to extrapolate heat flow. This is the main example, but I will directly focus on this so-called multi-proxy approach, which is using the similarity method, which is a statistical method developed by a researcher from Paris. This method had been developed. Okay, there is a tool developed by this researcher from Paris using this similarity method. And this tool is using two databases. The first one is the compilation of all of heat flow measurements available. In this tool, all the points of measurements are converted in a map with pixels associated with the heat flow value. The second database used is a compilation of geological and geophysical constraints. For example, you can have the age of ocean floor. You can also have the topography and the bathymetry. Actually, today we have more than 50 proxies in this database. It's just an example of what we can put inside the calculation. And the output of the calculation provides you a predictive heat flow map. Just to show you very briefly how it works, the calculation will associate each pixel of the surface of the Earth with its geological and geophysical constraint. If you have a pixel without any measurements, the calculation will search for heat flow measurements with the same characteristic, geological and geophysical characteristics. If you have all the same characteristic, you will have a better confidence of your prediction. These similarities lead to develop a quality indicator for the prediction. And here you have the map of quality. And what we can see is we have a very poor quality prediction along the ridges, because in that places you will observe very high variability of measurements, and usually it's associated to hydrothermal activity. The quality indicator is related to the standard deviation of the similitude identified. Here we have the prediction at global scale with a resolution of 0.5 degree. And what we can see is the highest value are located along the ridges, which is not surprising. What we can see is on the continental crust, we highlight very high variability in predictions. For example, in North America, you have all the west coast characterized by high heat flow prediction, while the west coast are mostly with low values. We can also see along the Andes the display that there is an important volcanic activity with high heat flow predictions. If I show you the map related to the quality of prediction, that we can see again is the worst prediction quality is mostly located all along the ridges. Again, it's not surprising, but that we can notice this represents only 8% of the surface of the map. So it's quite a good indicator to say the prediction is a really robust approach. Now, if we want to have a look on a specific area to make more detailed studies, if we only zoom on the global scale, the resolution is not so good. The map is very pixelized, and it's not possible to have a very detailed study. So the researcher that developed this tool proposed a local approach. And so if we have a look on this specific area, which is the Mozambique Channel, here you have the map compiling all the available data of the heat flow measurements. The colors are related to the value of the heat flow. The gray one are confidential data, so I don't provide the values. And here, the shape of the symbol and the color are related on the nature of the measurements and the age of acquisition. What we can see here is even if we have 166 available measurements, we have a very heterogeneous heat flow coverage. And in addition, we have very high variability in measurements. Here you have very low heat flow, and here you have a very high measurement. So we decided to proceed a local study on that area because it's very an interesting area due to the geodynamic context. Actually, it's an old oblique rift system, so we have many strikes with faults. So it's a good place to study the relationships between the localization of thermal anomalies and the activity of fault tectonic faults. For the calculation, we use only 14 proxies. I can explain later why, but I won't be too detailed in that talk. And we use, for example, topography and bathymetry. We use the compilation of the main tectonic structures, the localization of the active Holocene volcanoes, and the continent ocean boundaries, the sediment thickness, the nature of the crust, the Bouguer anomaly, the Curie-Point depth, and the free air anomaly. This is what we use for the calculation. And we can produce this type of maps. And with this increasing of the resolution, we can have a quite detailed map, which is allowing us to provide some clues about the relationships between thermal anomalies and tectonic structures. We have the quality map, and here it's a simplified map for highlighting the main anomalies. First, about the prediction, we have 70% of good and very good quality prediction, and even we have many orange or red colors. We have only 20% of low quality prediction, and again, this lowest quality are located near or at the place of high thermal anomaly predicted. For example, you have here the Comoros archipelago and in the Mozambique basin. In the Comoros archipelago, we know there is a study documenting the hydrothermal activities in that place. So it's not surprising to have a very high heat flow anomalies and high variability in values. Concerning our main question about the relationship between fault and thermal anomalies, what we can see here is a good correlation with the oriented northeast-southwest tectonic structures and the orientation of the high heat flow anomaly. At the opposite, we have this huge fracture zone, which is more correlated with low heat flow anomaly. So this is questioning why sometimes you have high value associated to tectonic structures, and sometimes it's high values. In that place, we can infer that we also have a link between tectonic structures and the localization of the high heat flow anomaly, but it's less clear than this area. We suppose that the tectonic structures which are seen are associated with low heat flow anomaly, and maybe they are associated to the downward wave paths of fluids circulation, while the active tectonic structures will allow the upward fluids. Yes, and in that study, we documented quite good correlation between the localization of heat flow anomalies and tectonic structures, with maybe the upward and downward wave path, but it's only predictive approach, and it's only view from the surface processing. We don't really know what it happens in there. Currently, we are working on another area, which is the Mediterranean region. Why? Because in the quite narrow space, we are in the western part very high heat flow predicted, and the eastern part very low heat flow predictions. So in that area, we are currently working to explore the effects of evaporative deposits on heat flow prediction. And because it's an area with many orogens, we want to explore the impact of tectonic record on these deposits. Because there is tectonize, there is occurrence of diapirs, and there is also a huge variability in the thickness of these sediments in these deposits. So it's a very ongoing project. But again, we want to explore the impact of tectonics on the thermal anomalies. But what is important with this approach? It's only surface approach. So if we want to have a look and better understand what is happening beneath the surface, we need to know. Yes, we need to know how it's working beneath the surface. But what is the currently model? Actually, it's more 2D view when you have mainly vertical fluid circulations with downward wave paths of fluid from using the return normal force, and when they are heated at depth, then they can go upward by, again, return normal force. But in this view, we completely avoid what is happening very down to the surface. And recent studies show the impact of ductile deformation on fluid circulation. When I say ductile deformation, I mean schistosity. And the schistosity allows two things. The first is connecting the brittle normal faults where outcrop at the surface, and then they can allow horizontal displacement of fluids. This involves or implies a lateral extension and a 3D view to better understand this type of hydrogeothermal systems. But how can we provide clues from what is happening in the surface? This is the importance of fossil systems. Indeed, due to orogenic processes, the deeper part of such system can reach the surface and can be directly studied. So I will now move on the fossil systems, and it's not so easy because what is a big problem with the fossil systems? It's the repetition of the Wilson cycle. And if you are repeating main tectonic events, you have the problem of the superimposition of the tectonometamorphic events. So it's a good idea to want to study the deeper part of surfaces of systems, but when they reach the surface, maybe they recorded many tectonometamorphic events, and the youngest one will erase the older. To present some evidences of fossil systems, I will focus on the Mediterranean region, where we can find many orogens with various geometry and their own dynamic evolution. Actually, today we have systems in quite blocked, but with the extensional basis. Here we have systems with collision dynamics, and here with a very extensive tectonic. But we can start the history of this region with the Mesozoic rifting, allowing the formation of several domains. And at the end of the Cretaceous, there occurred tectonic inversion with convergent dynamics. And this, all these subduction zone initiatives allow the formation of metamorphic rocks and, for example, the high pressure, low temperature units. When the specific subduction zones are involved with the slab rollback, there is a common age of all these slab rollback in Mediterranean region is 35 million years. In my talk today, I will present you two case studies. The first one is French Alps, and the second one is located in the Hellenid context. The first one is mainly to show you how it can be difficult to get information about the old phases of some metamorphic rocks. And the second one is more focused on the relationships between tectonic structures and fluid circulations. So the first one is focused on the Dora-Maira Massif, which is a stack of tectonometamorphic units by basal aggression during subduction of erosion passive margin. It's located in the southwest part of the Alps, and this complex is composed by or constituted by continental rocks metamorphosed in ultra-high pressure, low temperature metamorphic conditions. Actually, for the ultra-high pressure, you can see here the star marked the augment of quasites. So the ultra-high pressure. We can see also an increasing from low blue schist facies toward the ultra high pressure metamorphic facies. Why we focused on this specific complex is because we can observe unusual composition comprising lenses of continental and oceanic lithologies embedded in calcareous matrix. Remember, I said this Dora-Meira massif from here to here is a continental composition. So it's quite unusual to find units with oceanic lithologies and mixed with continental lenses. These units are described as shear zone. Here you have the first one and this one. And here you see you have the calcareous matrix with lenses with composition of sometimes metabasalt, serpentinite, and micaschist. These shear zones are interpreted either as tectonic mélange or as a photolith heterogeneity. When I talk about tectonic mélange, it's more related to the formation at the subduction interface during exhumation of metamorphic units. When we are talking about photolith heterogeneity, it's more related to the pre-structuration before the subduction initiation. Here you have just a view of the field area, and what is sometimes a little complicated is the occurrence or the number of outcrops and the quality of outcrops. In addition, the slope is quite steep, so sometimes it's hard to go where you want. If we have a look on the structural measurements, here you have the compilation of the schistosity measurements for the Shima-Vili unit, this shear zone. And what we can see is schistosity gently dipping towards the west, southwest, until the south direction. If we have a look on the San Damiano unit, it's the other one shear zone here, you have gently dipping schistosity toward the southwest and the south. And if we continue to move toward the east, in this unit, we measure schistosity dipping toward the southwest and the northeast direction. If we combine all the stretching lineations obtained in this in all these units, we see northeast southwest orientation. And all these measurements allow us to say we have a large southwest dipping knob stacking with a dominant northeast southwest transport direction. In addition of this northeast southwest transport direction, we have the evidence of quite big isoclinal faults. Here you can see the faults. Also oriented, also showing a direction of deformation oriented northeast southwest. All these measurements allow us to modify the cross section from the André Michard PhD thesis in 1966, and here we have the structure of the first shear zone with calcareous matrix and lenses, and the structure with the large isoclinal faults here, and the same for the second shear zone. If we if we try to characterize the thermal structure of this area, here we compile all the available data acquired with Raman spectroscopy on carbonaceous material, and we have data from Michard. It's a published work from 2022, and here you have our data separated when it's appeared in the matrix or in the block. And what we can see is an increasing of the maximum temperature from the west toward the east. You have the color related to the geological unit of the map. Another thing is if we have a look on specifically the shear zones, this one, the temperature range is mostly comprised between 440 Celsius degrees and 500 Celsius degrees. But it's still a work in progress. We acquired new data and we have to define these estimations. Now I will show you some results from the petrology and PT estimations, and I want to show you a typical outcrop of the interstratified metaturf or metabasalt in this shear zone. We have typically quite thin metabasalt layer, transition zone, and then a quite white marble. It's not easy to see, but the marble is mostly from this color. I wrote on this slide metapilobasalt because sometimes we can well preserve the structure of pillows. Here you have a white dashed line, the contour of the pillows. If we try to do some PT estimations of in these shear zones, it's not really easy because I don't really show you, but it's very highly retrogressed rocks. But if we start with the Shimaluni shear zones, this one, we have this mineralogical composition with sometimes quite big blue crystals and inclusion of rutile and zircons. We were not really able to find a stability domain with this mineralogy. But we plot data acquired in the matrix with RSCL. Keep in mind these are coming from lenses, from this green part, and here it's from the matrix, so the blue part of the shear zone. If we do the same with the other shear zone, the San Damiano shear zone, we were able to provide a quite wide stability domain. Here, this one. And if we plot the measurement on this block by the RSCL method, we can reduce the range of temperature. But concerning the pressure estimation, we are still between 22 kilobars and almost 12 kilobars. So it's too wide. We need to refine the PT estimations. That's why I wrote work in progress. What is important to note is the lenses seem to record higher maximum temperature than the calcist matrix, as can be observed here. If we want to compare with other similar units, we can do this work on the Keras unit here, out of the Dora-Mara massif. And what we can see again, we have a difference between the stability domain obtained for this lens and the maximum temperature recorded in the matrix. This is for the retrograde metamorphic condition. It's not the peak of metamorphism. And it is important to note, even if we have quite a difference between the matrix and the lenses, this unit is described as resulting from the protolith heterogeneity. So, as preliminary conclusions, we can say for these shear zones, we have both sedimentary and tectonic melange origin. Remember when I show you a picture of an outcrop, we have an heterogeneity of the volcano sedimentary protolith of the shear zones. But we also documented isoclinal folding and shearing, resulting in abstracting transposition and tectonic melange with hectometer scale displacement. I will not detail the geodynamic evolution, but just to know that we infer that the development of the schistosity, the main schistosity, and isoclinal folding are during the subduction dynamics and during the exhumation of these metamorphic rocks. Then, during the collision, you embrace with a backstressing of the high pressure, the ultra high pressure, low temperature metamorphic rocks. And it's in that moment that you develop the second fold that I didn't show you. But yeah, it's just to present you quite preliminary conclusions. For the second case study of these fossil systems, we moved toward the Greece area, and here this area is characterized by a northward subduction of the African plate beneath the Eurasia, and you have basal accretion in the far domain. But since 35 million years, you have a southward slab retreat, inducing background basin development, the Aegean Sea mostly, and associated to this slab retreat, you have the final exhumation of high pressure, low temperature metamorphic rocks, which can be observed in the northern part of Kisira Island here. And this metamorphic unit is called phyllid quartzite. I will show you our results about this metamorphic unit. So here you have the detailed geological map of the northern part of the island. All the violet colors are related to this phyllid quartzite metamorphic unit. And we observe in this unit several faults or shear zones associated with development of foliated cataclysite that affect this phyllid quartzite unit. Here you have the synthetic cross-section from here to here, and I selected two samples coming from that place and that place. I start with the white one. This is cataclysite, foliated cataclysite, sorry, and all the green or light brown colors are tourmaline. Here you can see, and you have two types of tourmalines. The first one is a subhedral crystals, which are zonated and different from the tourmaline in the matrix. Then you have white mica layered with hematite crystallization. For the mineralogical composition, it's quite a simple one. And we have quartz, feldspar, tourmaline, white mica, and oxide. If we have a look on the other sample coming from the north, this one is interesting because is very close to the main composition of the metamorphic units of Philip quartz. It's foliated cataclysite, but not really pervasive transformed. We have the quartz, feldspar, white mica, and oxide. What we can see here on this SEM image is the feldspar are brutally deformed, which is not the case for the quartz. If we compare the measurement obtained on white mica, what we can see is for this sample, it's a violet measurement, it's quite homogeneous. While the other one, the red colors, are very heterogeneous. We inferred it because the white mica crystallize with hematite, and we have a very high iron content in those micas. So, as preliminary conclusions, we can propose a chronology inferred from the tourmaline bearing sample. So first, we have the crystallization of pyrites and tourmaline with subhedral crystals in reducing conditions. Then we crystallize all the matrix with tourmaline but anhedral crystals. And then we have the oxidizing conditions, the destabilization of pyrites, and the crystallization of the white mica interlayered with hematite. Concerning the deformation, we see that quartz show pressure dissolution deformation. That means we are higher than 300 Celsius degrees. While feldspar show brittle deformation, that means temperature lower than 500 Celsius degrees. This is confirmed by measurements obtained by RSCM. And we are trying to propose PT estimation for these metamorphic conditions. And what we obtain is a range for pressure between 7 and 3 kilobars, which is in good agreement with this study from Jolivet made in Crete in 1996. They proposed for this metamorphic episode pressure between 6 and 2 kilobars. So it's quite in good agreement. The temperature is quite in the lower part of our range, but it's in good agreement. What's next? We are doing argon dating on several mineral phases to maybe be able to date the first increment of the fluid circulations, because we want to date the adularia, and then the last step of the activity of these shear zones with white micas. We try to date tourmaline, but it's very hypothetical thing. And the next step is to provide more precise PT estimations and do fluid inclusions on veins, because here what we can see is you have not a concentration of veins just at the shear zone emplacement. The veins are going very far from the main tectonic structures. So it's interesting to better constrain how the fluids are displacing from the tectonic structure into the schistosity of the main metamorphic rocks. I finished. Thank you. Thank you very much.
Questions. Preguntas, quieren pasar en español y la conclusión. Vamos a aprovechar todo tu traducción. Professor, thank you very much. I heard you bring Spanish.
Yeah, no problem.
Me parece muy interesante, un trabajo muy interesante. Me gusta mucho esas predicciones y también el tema de malfluidos, ¿no? Que es muy importante y que nosotros, digamos, por trabajos acá en Medellín, en Colombia, del 2013 al 2022, casi 11 años, 10 años, más o menos. Vinimos haciendo análisis de inclusiones fluidas en muchas venas, ¿no? Que son paleofluidos. Algunas de estas venas las tenemos declaradas y otras no, que obedecían a mineralizaciones. Entonces, hay datos que se tienen acá, ¿no? Que se podrían utilizar en un estudio de fluidos y cómo lo vería la profe. Esa sería como la pregunta.
Yeah. Professor Rolano has been working in several projects since 2012 for more than 10 years. Doing pairing data on fluid inclusions, veins. Some of those veins have also age information. And well, first you said that it's very interesting what you're doing. And it would be great to like take that database and make on our research. Well, starting with the database, do some additional research here in Colombia. So he's asking, ¿cuál es el plan de ellos? ¿Cómo? La pregunta es, ¿cuál es el plan?
No, que hay una información que me da. ¿Cómo lo vería cómo lo vería la profesora en este tema?
Yeah, so how do you see that maybe having access to the database and using that for
For the predictions or?
Yeah, we're doing some work similar to you.
Yeah. The predictions, okay, I present and I always said it's researcher from Paris that developed this tool, but during my postdoc in Paris, I was a user and a part of developer of this tool. So I have all the databases and I'm taking care about the updates of this database. Yeah.
Right, but this is a fossil systems.
Yeah. The problem is we are dealing only with present constraint because it's surface present data. Yeah,
but he's asking about the fossil research studies.
Yeah, it's
having that as a base.
Yeah, it's the challenge because it's actually, I think it's the only way to learn about how it's working at depth. But it's mainly to better characterize the systems and then to say, okay, we can maybe build some proxies related to what we provide as a result. It's not based directly on fossil systems, but you have to transfer to the present systems. I don't know if I'm clear. Yeah, it's a challenge.
No, quiero tomar una pregunta más con respecto a la base de datos actual acerca del tubo de calor. Pues que los sistemas fósiles no van a decir, ya no sirven para actualizar esa base de datos. Ella está trabajando en esa base de datos. Pero digamos que no hay forma de llevar esos datos fósiles a lo que hay ahorita, ¿sí? Que hay pues muchas variables ahí que influyen. Pero voy a decir algo que dice ella. Ella dice, va a comenzar a trabajar en venas en la corriente central, ¿sí? Para hacer medidas de inclusiones fluidas, mirando los sistemas fósiles en la corriente central. Que yo de pronto pienso que sí puede haber cierto interés en mirar dónde tienen los datos ustedes en estudios como punto de partida, pero si quiero hablamos de eso ahorita que sí, que lo vamos a hablar por la tarde. Si ahorita que haces no, y que se lo que sí la idea está en el campo. Tallos, todo profesor Morano, y
Yeah.
¿está puede ser?
Sí, entiendo un poco esto.
Ok.
No puedo hablar.
I have one. I'm very interested in doing temperature determinations using around correlation material. My question is, I saw that you have a good amount of data on the first project, the first area that you did, or in Western Europe.
Yes.
And how do you determine those temperatures? Do you use standard? Do you calibrate internally your data with
No.
other
Yeah, there is a
temperature?
Yeah, there is a calibration depending on the range of the temperature you want. And it's only a formula.
Okay, but the calibration is not using the standard. It just
No. It's
Standard.
through the Raman effect.
Okay.
And each spectra reflects the degrees of organization of the organic material. And with this formula, you can calculate the maximum temperature related to this degree of organization.
Okay.
But you don't use standard.
Okay. Because I see some papers where they use internal calibration with data from other thermometers within the same database.
For this method, you don't need standard.
Okay. Good.
But it's specific to this method.
Okay. What is the maximum temperature you can estimate with Raman?
I think until 600 Celsius degrees, it's okay. You can reach 620 Celsius degrees. And the lowest, there is a calibration in development for very low temperature. But for now, what is published is only around 200 Celsius degrees.
Okay. And
So
the
between 2 and 6.
The last question, so that is the you do one measurement per sample, or you do like a bunch of them, so the statistical driven?
Yeah, this is depending on the operator. Some use only 10 acquisition on the thin section or by sample. Me, I most around 20 because, the Raman spectroscopy is based on the organization of the organic material, but it's it's a permanent process. You cannot go back. So what you are recording is always in the maximum temperature recorded by the sample.
Okay.
If later you have lower temperature, you won't be able to record that. Okay, and sometimes you can have heritage on samples because you can have organic material coming from metamorphic, high-grade metamorphic protolith. But then, due to orogenic processes, you will record in newly formed organic material a lower temperature. So I'm part of a user that acquired mainly 2025 spectra to see if there is this heritage in samples. But it's quite fast. I don't know, in one day, depending if you have many or very rich sample with organic material, but you can make between 6 and 10 samples per day. Then you have to make a treatment on spectrum, but it's okay.
Preguntar sobre la metodología de medición de Raman por esta temperatura.
entre 200, 600 grados más o menos.
De 200 a 620 máximo. Bueno, thank you very much. Excellent.
You're welcome. Thank you.
Ahora hacemos otro y